Hello everyone, and welcome back to another video. It's been a while, and it's because I have personal stuff going on in real life, or should I say personal life. But if you stalk on my Steam profile, you can see that I have uploaded several builds. The one that I would like to point out is the car and the flyer. But this video is specifically for the flyer, and I will make a video about the car soon. So let's get into it. So, if you remember my last video, I showed you guys some suspension glitch free flyers, but the problem is, the technologies they have are very dated from now, except for the pulsar. But there is no denying that they are also decent flyers. So a few months ago, Kein released a new flyer that is similar to the pulsar, but it's a lot better in most ways. But the current time being, this is actually the most advanced civilian flyer uploaded on the workshop. But let's get straight to my flyer. My flyer isn't any better, but it is basically my take on properly making a flyer with the help of Kein Anderer. Because the previous flyer that I had made is a very much mess, so I very much wanted to make a better one. But I guess I could say this flyer is average for modern tech. It has features that I want to explain with Kein because I'm usually bad at explaining stuff. So let's start off on how I built this flyer. A few days after the release of Photon, I had started making a flyer because I wanted to fix all the mistakes I made on the previous flyer. One thing I noticed with the Photon is the rotors. And what I realized is, I don't need all 4 rotors. So now, if you're new to flyers in this game, what exactly is the purpose of the rotors? Well, I will actually let Kein explain.
When it comes to flyers, like this one that you can control on a lot of axes at the same time, including being able to control road, pitch and yaw independently. And especially a flyer that would push faster speeds like this one, it can be quite a handful to control. You would notice if you ever build a flyer like this. But one thing we can do to make it a lot easier to control a flyer like this, or any kind of flyer that is pushing faster speeds, is being able to automate some systems. And one technology we have for this is what we call inertia control, which in our case only automates inertia control and rotation axes, because that's the only thing we can really detect in this game. And this flyer uses 2 types of technology, rotors and deflectors, but I'll first cover rotors here. So the core principle that we need to understand for inertia control based on rotors is gyroscopic precession. That's the main effect we're using. And this effect exists in real life as well. When it comes to a single rotor, you can always, it will always work on, or it will always apply precessive torque on 2 out of 3 axes. It can't apply it to all 3 at the same time. And it's always the 2 axes that are perpendicular to the axes on which the rotor is spinning on. So let's say the rotor will be spinning on the green axis, or around the green axis. We would have precessive torque on both the red axis and the blue axis. Or at least potentially. In this flyer, the setup that we'd have, as we have the rotors mounted on the vertical axis, this will only apply precessive torque on roll and pitch. So when we're applying roll and pitch, it will effectively continuously fight that roll and pitch, which we are using as a form of speed limiter, as well as a form of automatically decelerating it to bring it back to a speed of 0. Again, to simplify flying around. When it comes to gyroscopic precession, it has 3 main variables that are relevant, with those variables being the speed with which the rotor is spinning at, the mass of the rotor, as well as like the radius of where the mass is placed around the axis of rotation. Or in other words, the speed of the rotor, the amount of mass the rotor has, and the diameter of the mass on the rotors. And when you want to make really efficient rotors, you're effectively bottlenecked to just being able to push the diameter, as adding more mass will of course make the flyer slower, and speed can only be pushed so far. And as we are of course fighting inertia with the inertia control system, you effectively end up wanting a ratio between the precessive torque the rotor can apply and the inertia that the flyer has. And you often end up with a design where the rotors will actually be outside of where most of your of the mass on the body is, relative to the rotation axis. In this case, we can see most of the thrusters being in the center, and the rotors being around those to keep the processive torque a lot higher, relatively speaking. This way we can actually make way lighter rotors, while pushing the same kind of processive torque you'd have with smaller rotors that are a lot heavier. And again, weight reduction is very much key when you want to go faster. So this is effectively what you want to end up doing. With this design, we also have 2 counter-rotating rotors, as we are powering it with bearings that are mounted on the flyer body itself. It's important that we have them counter-rotating to make it actually balanced on yaw. Otherwise, you'd have the whole vehicle spin at yaw speed. And yeah, actually, this is all we need for rotors, I think.
Now, Kein also pointed out that if I add vectoring, I'll also have a better thrust utilization. You can also notice that the thrusters are placed in a way that makes them centered on the grid. This is to help me align the center of mass without doing too much trial and error with the center of mass tuning. Another thing is, this flyer I made is very much well balanced than the previous flyer I had made, which I considered a blue whale with thrusters. While I was building the flyer, Kein also suggests that I should at least have inertia control on my yaw, because normally it doesn't have one. And the flyers we usually see in the workshop that isn't made by Kein typically doesn't have inertia control on yaw, because all flyers that have rotors placed vertically can only have inertia control on roll and pitch. So I have 2 options. One is having rotors placed horizontally, which would significantly make the flyer bigger height-wise, and the other option is to have deflectors. Now, I chose to have deflectors, but what does deflector mean? Well, I will let Kein speak again.
The rotors that we are using are already a form of inertia control we're using on this flyer, and it is a type of inertia control that has existed for a very long time. However, it's not the most efficient design you can necessarily use when it comes to power to weight, as you'll always need a minimum mass to actually have processive torque. And you can effectively see it as needing an external power source, and the weight, unlike the actual gyroscopic precession that the rotors have to apply that torque to the body. If you want to save that complexity and that mass, there is another technology we have for inertia control that is going to be more efficient for both of these things. And that is what we call a deflector. An example you can see on the back. But before I show off the design on this flyer, I will generally show off what this what a deflector is. So the deflector is at least what we call it, because it's not an effect that exists in real life at all. It has to do with the way the game handles gyroscopic precession, and you can see it as the kinematic inverse. And the interesting thing about it is when it comes to it spinning on a given axis and then being spun around another axis on the actual flyer body, it always moves on the axis around which it is spun on the flyer body itself. So in this example, we have this pipe here spinning on a bearing that is mounted on the vertical axis, and then we have a steering bearing that will rotate this around, let's just say, the transverse axis for this example. And you can see it actually moves side to side in a non-rotational kind of fashion, being exactly the same axis as the axis around which it is being rotated on what would be the body of the flyer. And the way we can utilize this is as a form of angular speed sensor. There are multiple ways you can actually implement this. You could even make a fully mechanical system, but the design that the flyer uses is actually primarily electronic system, where you use sensors to pick up a mechanical piece that moves up and down under yaw speeds. And then we use the internally mounted thrusters to decelerate the build when you're not applying a yaw speed anymore, to automatically decelerate it. As an example, let's say you give it a yaw speed in one direction. I maintain that yaw speed, as I can do here. It's not going to be active at all, because I am actively giving it a yaw input. But the moment I let go, the sensors will actually transfer an input to the thrusters that would be rotating it in the opposite direction until the sensors are off again, which can only be the case if the sensor or like the mechanical piece is in a position where the speed would have to be 0. As you can see here. And this lets us use the internal like power systems we have already, being the thrusters, instead of needing an external power source. This saves us a lot of weight and size compared to a rotor. I mean, you can already see it just looking at the flyer if you compare the rotor's physical size and weight with the concrete at the ends compared to just this little piece here. Also important to mention that weight is actually not relevant to the deflector piece itself. It's only the offset of the mass from the joint, which makes it actually fully mass independent, though we do need a certain mass just because of the geometry of the physical detection piece to make sure the sensor detects it properly. Similar to rotors, a deflection sensor always works on 2 axes. It can never work on 3. Making a purely one-dimensional system is actually impossible, but we only need to actually detect 1 dimension, which is what we're doing here. But because it will also move, in this case, on the pitch axis, and since we want your inertial control to still work under pitch as well, we have a bit of a bigger size shape on here to make sure that that can still detect even if it has moved side to side a bit. We also have a second sensor, if you take a look here, for both directions, which we can use as a speed limiter. Since it's a speed detector, this whole system, it's not just limited to being used for inertia control, but you can also use it for a type of speed limiter that effectively cuts the inputs that you're giving the flyer through A and D for yaw, at least in this case, by just turning off those inputs when the speed is too high. And then it will effectively fluctuate between being on and off, maintaining a speed below the maximum that you want. So this gives you a lot of versatility when it comes to setting up the rotation speeds to be exactly like you want. Mechanical system can even give you a way more ideal function out of these, because currently these will only really be on or off with a single stage. If you want more stages, you'd have to add more sensors, and if you want a fully continuous function, we would need to add infinite steps. A mechanical system can completely bypass this, but you're of course trading this for mechanical complexity, as you need to directly have it attached to rotating thrusters with a linkage. Another thing that is relatively relevant when it comes to these is the actual shape it has. This is following effectively a 3x3 shape, just so we can have the sensors on the grid without needing extra joint separation. But you'll also notice that it's not actually a perfect circle. And this is not that big of a deal, because that does mean that at smaller speeds we can actually have the sensor be pulsed instead of just being fully on, giving us something a little more variable than just an on-off input. And that makes it a bit more forgiving when it comes to lower speeds. And that is this is effectively the main info you need to know when it comes to deflectors. There's a lot more you can cover, there's a lot more we can explain as well. On the Discord server, we're willing to help out and answer more questions that exist with this. I've just given a very basic overview of what these do and how they are generally implemented. There's a lot more behind these effects that I have not covered in this video.
Yeah. If you guys want to see the Discord server, link is in the description, and you can join there if you guys want to see or want to make a flyer or something like this. We can help you and stuff like that. And yeah. Now that I have the deflector, I just have to make the electronic system for it. The problem is, I have to face my weakness, which are logic gates. Well, thankfully I had convinced Kein enough to give me the logic gates, even though it's simple to build the logic. Well, speaking of logic, Kein also suggests that I should make a platform for the electronics in the flyer. It took me hours to properly configure it, and Kein was legit mocking me for struggling. Well, I mean, to be fair, my skills aren't designed for logic gates. Oh, what a terrible excuse. So anyway, that's pretty much on how I built this flyer from the ground up. Like I said before, this is my first time making a flyer properly, so let me know down in the comments if you want me to actually make a higher performing flyer, similar to the Photon. So yeah, thank you all for watching and I'll see you in the next video.